All right, welcome to chapter 3, where we're finally going to talk about why we care about derivatives other than just a tangent line. We are going to start off with extrema on an interval, section 1. So, the definition of extrema. F is defined on an interval, I, containing C. F of C is the minimum of F on I when F of C is less than or equal to F of X for all X in I. What that means is F of C, so that's my Y value, F of C is less than F of X. So this particular Y value is less than every other Y value in that interval. So that means it's lower, the other ones are higher up in my interval. There is my minimum. F of C is the maximum if F of C is greater than or equal to F of X for all X in I. Same exact thing except flip the other way. F of C is higher than all the others. The minimum and maximum of a function are the extreme values or extrema. So extreme values, extrema, same exact thing, on that interval. The minimum and maximum of a function on an interval are also called the absolute minimum and absolute maximum, or global minimum and global maximum on the interval. So absolute and global mean the exact same thing in this case. It just depends on the problem, the textbook, the video, whatever, which term they'll use. And then extrema can occur at interior points or endpoints. If the extrema are at an endpoint, we call it an endpoint extrema. So that would be if, I remember, we're just in an interval. So we start there, maybe end there, right? We got, I've got a global maximum right here because it's higher than everything else, even though it's at the endpoint. So that gives us the extreme value theorem. If f is continuous on a closed interval, a to b, then it has both a minimum and a maximum on the interval. So it has to be continuous, right? No jumps, holes, gaps. It will have a maximum and a minimum on an interval. Realize this doesn't mean the entire function on its entire domain. It means I'm cutting it off on the left, I'm cutting it off on the right. There has to be a top, there has to be a bottom somewhere. So, using a graphing calculator, we're going to find the extrema of this function. So we take out our handy-dandy graphing calculator, and we say, all right, there we go, y equals x squared minus 4x plus 5, graph it. Cool. I'm on the interval -1 to 3. So I only care about -1 to +3. So I'm going to have an absolute maximum and absolute minimum in that interval. So we calculate. I can see that there's a minimum, right? So here, get on the other side of it, press enter, guess, press enter. 2, 1 is my minimum. So I have a minimum at the point 2, comma 1. Because that's lower than everything else in the graph. 2 is between -1 and 3. Cool. Now I can use my calculator to easily find the maximum. It's either going to be at -1 or 3. It's going to be one of those endpoints. So I can hit second calculate value and just type in x is -1. Y was 10. We'll do the same thing for our other endpoint. Value when x is 3, y was 2. Well, 10 is obviously bigger than 2, so my max is at -1, 10. So remember, we always need to evaluate those endpoints, right? F of -1 was 10. F of 3 was 2. 10's bigger. There we go. All right, let's try the next one. Y equals x to the third power this time, minus 2x squared. X minus 2. And we are on the same interval, right? -1 to +3. So I look at this. I might have a max here, a min here, but we're looking just absolute maximums and minimums. So the first things we want to calculate are any that look like they're maxes or mins. So second calculate. I see a max there. All right, I've got, guess, there we go, -0.535, comma, -1.12. So I'm going to write that point down. my bad, okay, negative 0.535, comma, negative 1.121. And then I'm going to calculate this minimum that I see. (1.869, negative 8.065). All right, but then also remember that the maxes and mins can occur at the endpoints. So I'm going to calculate each of those. Value at negative 1, I get negative 1, negative 2, and value at 3, I get 3, negative 2. All right. Now I have to decide my max and my min in this interval. Well, the highest it goes, the biggest of these numbers, is negative 1.121. So my max is at negative 0.535, negative 1.121. My minimum is definitely the negative 8, so my minimum is at 1.869, negative 8.065. So make sure that you always check those endpoints also. So the definition of relative extrema. Those were absolute extrema we just talked about. If there's an open interval containing c on which f of c is a maximum, then it is a relative maximum. Or you can say f has a relative maximum at c, comma, f of c. Like I just said, there was a max at 3, 2, whatever those numbers are. If there's an open interval containing c on which f of c is a minimum, then f of c is called a relative minimum of f, or you could say that f has a relative minimum at c, f of c. Relative maximums and minimums are sometimes called local maximums and minimums. So, the big thing here, the difference between extrema and relative extrema. Extrema are on a closed interval. So we include endpoints. The endpoints could be the extrema. Relative extrema are in an open interval, and these can't be the endpoints. All right, relative extrema are oftentimes used when we're talking about the whole graph and not just a specific interval. All right. We're going to find the derivative at each extremum shown below. So the plural of extrema, extremum. So relative extrema. We want the derivative. All right, I got this funky looking equation. First of all, I'm going to rewrite it. I'm going to multiply that 9 into the numerator because I like it better. To get my derivative, I use the quotient rule. Derivative of the top is 18x times the bottom minus derivative of the bottom times the top all over the bottom squared. All right, let's simplify that. 18x to the 4th power minus 27x to the 4th power plus 81x squared over x to the 6th power. Honestly, I don't even need to simplify anymore, but I'm gonna. I have 18 minus 27 is negative 9x to the 4th power plus 81x squared over x to the 6th power. And I can divide all of these by an x squared. So I'm going to do that also. Negative 9x squared plus 81 over x to the 4th power. All right, but I want, that's f prime of x. I want f prime of 3. So f prime of 3, negative 9 times 3 squared plus 81 over 3 to the 4th power. I don't feel like typing that stuff out or doing it in my head, so negative 9 times 3 squared plus 81 divided by 3 to the 4th power. I got 0. So f prime of 3 was 0. All right, let's look at the next one. I want the derivative at 0, 0. Well, there's a sharp corner there. So technically the derivative does not exist. Does not exist at x equals 0 because the derivative from the left and from the right aren't the same. Left hand and right hand derivatives aren't equal. So there the derivative did not exist. And now for the sine of x. Well, the derivative of sine of x is cosine of x. We're not using that marker apparently. So we want the derivative at pi over 2. Well, the cosine of pi over 2 is 0. And then we need the derivative at 3 pi over 2. So the cosine of 3 pi over 2 is also 0. We could try all the other relatives, maxes and mins, but notice that they were 0. So that tells us a critical number. F is defined at C, all right? It has to be defined there. Can't be a hole. If f prime of C equals 0, or if f is not differentiable at C, then it is a critical number of f. So anywhere the derivative equals 0 or the derivative does not exist is called a critical number. And critical numbers are very important because relative extrema only occur at critical numbers. If f has a relative minimum or relative maximum at x equals c, then c was a critical number of f. So this is important because it tells me that relative max or min can only occur when the derivative equals 0 or derivative does not exist. All right, that helps us a ton with finding our maxes and mins because we can set our derivative equal to 0. So, finding extrema on a closed interval, guidelines for it. To find the extrema on a continuous function, we find the critical numbers, which is the derivative equal to 0 or does not exist. We evaluate f at each critical number, so f of a, f of b, f of whatever. We evaluate f at each endpoint. The smallest one is the minimum, the greatest is the maximum. So let's look at how that will work. I want the extrema of this function on the interval -1 to 2. Well, extrema can only occur at the critical numbers. The critical numbers are when the derivative is equal to 0, so we need the derivative. The derivative here is 12x cubed minus 12x squared. This exists everywhere. It's continuous. So set equal to 0. I'm also going to factor out a 12x squared. Leaves me with x minus 1. So my solutions are x equals 0 and x equals 1. So my options for extrema, I actually have 4 possible points. X could be 0, x could be 1, or these 2 endpoints. X could be -1 or x could be 2. Now we need to evaluate the function at those points. Please be careful, you're not evaluating the derivative there, you're evaluating the function. So f of 0, 3 times 0 to the 4th minus 4 times 0 cubed is still 0. F of 1 is 3 minus 4, which is -1. F of -1 gives me 3 plus 4, which is 7. And f of 2 gives me, let's see, 2 to the 4th power is 16. I have 3 times 16 minus 4 times 8. Calculator, what am I doing? That is 16. There we go. Now we can say what our maximums and minimums are on that interval. The maximum is the biggest, so 216. The minimum is the smallest. So smallest y value was -1, so that's 1, -1. There we go. So let's try this one. It gets a little trickier here. F of x is this. We want the interval -1 to 3. Well, we want the derivative first. F prime of x equals 2 minus 3 times 2/3. X subtract 1 makes it -1/3 power. All right, let's rewrite that. 2 minus 2 over the cube root of x. That's what I got going on. So the first thing, x could definitely not be 0. So that's a critical number. Because that would make a denominator of 0, and I don't want that. Now I'm going to set it equal to 0 and solve. You may be looking at this and saying, oh, Miss Dupree, that's terrible. It's fine. Let's add this over, because I like positive numbers. I now have 2 over the cube root of x equals 2. Then I'm going to multiply the cube root of x to the other side. Because now I have 2 equals 2 cube root of x. I divide by 2. 1 equals the cube root of x. I cube. I get 1 equals x. So my next critical number is 1. And then remember, we always have to test those endpoints, -1 and 3. Plug each value into the original function. 0 would give me a value of 0. -1, let's say I don't feel like thinking. Calculator time. 2 times -1 minus 3 times -1 to the 2/3 power. Make sure you put that -1 in parentheses when you raise it to a power. But we get -5. Whoopsie, I skipped one. How about +1? I'll just delete the negatives on here. I get -1. There we go. And then I need 3, so I'm just going to retype that with a 3. -0.240. All right, that means our maximum, the biggest of these values, is 0. So max at 0, 0. The minimum, the smallest, is that -5. So my minimum is at -1, -5. And there are my answers. Now, a trig function. Find the extrema of 2 sine of x minus cosine of 2x. We start off the same way that we've started all of them. We take the derivative. So f prime of x equals 2. Derivative of sine is cosine of x minus derivative of cosine is negative sine of 2x. But remember, we need the derivative of the inside here, which is 2. So really my derivative is 2 cosine of x plus 2 sine of 2x. Now here's where it gets wonky. We could guess and check, I guess. Or we can think way, way back to trig identities. And remember that the sine of 2x is equal to 2 sine x cosine x. So I'm going to replace that. 2 cosine of x plus, well, 2 times 2 makes it 4 sine of x cosine of x. And I want to know when it's equal to 0. And the reason for doing that is because now I can factor out a 2 cosine of x. I have 1 plus 2 sine of x. So that means the cosine of x was 0, or the sine of x was -1/2. All right, we're just going between 0 and 2 pi. So the cosine of x is 0 at pi over 2 and 3 pi over 2. The sine is -1/2 at 7 pi over 6 and 11 pi over 6. Those are my critical numbers. Now we calculate each coordinate. Remember, we go back to the original function for each of these. So I have pi over 2. If I plug pi over 2 into my original function, you know what? calculator it is, right? Make sure I'm in radian mode. Perfect, okay. 2 times the sine pi over 2 minus the cosine of 2 times pi over 2, 3. All right, 3 pi over 2. I'm just going to take that same exact equation. I'm going to insert a 3 in front of my pi. Negative 1. 7 pi over 6. Same thing. Just going to change the 3 pi over 2's to 7 pi over 6. Negative 1.5. And 11 pi over 6. I have negative 1.5 again. And never forget your endpoints, 0 and 2 pi. Zero, delete, 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 delete. 0, delete, 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 delete. Negative 1, almost done, 2 pi. If you remember, oops. There we go. The derivative, or the value at 0 will be the same as the value at 2 pi, but just to show you, it's also negative 1. Oop, there we go. So the greatest of these is the maximum. That would be pi over 2, 3. The minimum is the smallest, and notice that we have 2. They're shared minimums. 7 pi over 6, negative 1.5, and 11 pi over 6, negative 1.5. Since they are the same y value, they're shared. All right, now you have an assignment to try on your own. You have the Extrema worksheet. Do your best. We will talk about questions if we need to. Good luck.